Hello everyone, my name is Jesse Dodge, and today I'll be talking about RNN architecture learning with sparse regularization. This is joint work done with my co-authors Roy, Hao, and Noah. So in modern NLP, many of our results are pushed forward by large neural models that we empirically find perform well at our tasks. So imagine this is a large neural network that perhaps could be slow to train or have slow inference, but has a lot of modeling capacity and so empirically does well. Smaller models with fewer parameters don't have some of those drawbacks, so they can train faster, perform faster inference, and be smaller on disk, so you can save more checkpoints, for example. So we can ask ourselves, is it possible for us to retain good performance while using a smaller structure? And in this talk, we'll find the answer to be yes. Specifically, we'll use sparsifying regularization applied to a class of models known as rational RNNs. And we'll be learning the weights in those models and the model structure at the same time. So as an outline, first we will discuss rational RNNs, then our technique for sparsifying regularization, and finally present some experimental results. So rational RNNs are all around us. A number of models that have been published in recent years are within the broad class of rational RNNs. I've put a few up on the slide here. So quasi-recurrent neural networks, simple recurrent units, and one-layer convolutional neural nets are all examples of rational RNNs. They're a type of recurrent neural network, which many of you are familiar with recurrent neural networks. So here we denote some input string X, which is comprised of tokens, that's fed into a hidden layer H, which then produces some prediction Y. The difference between general RNNs and rational RNNs is that the hidden layer within a rational RNN has some internal structure. And the key advantage of this internal structure is that rational RNNs admit a one-to-one correspondence between the recurrent structure and a set of weighted finite state automata. So to make that more specific, the hidden state update for rational RNNs can be written as the forward calculation of a set of WFSAs. Another way to say all of this is that we have a single model and it can be viewed through two different lenses. First, as an RNN, so you can implement this model in your favorite deep learning package. And also, you can view that same model as a set of WFSAs. So for the majority of this talk, we will primarily be considering the WFSA view, but remember that this does correspond to an RNN like many of us are familiar with. I don't have time for a more formal introduction today, but you can find one in Schwartz et al. 2018. So one key property of these models is that within the WFSAs, each transition is parameterized by a different set of parameters. And so we can ask ourselves our motivating question once again. Is it possible for us to remove some of these parameters and still retain good performance? And like I said earlier, we'll find that we can. So we'll dive a little deeper into these model structure. Here on the left, I've written out some example parameters. So W11 is the set of parameters which parameterizes the first transition in the top WFSA on the right. And W12 is the set of parameters which parameterize the second transition in that top WFSA. And these parameters are typically learned using some standard loss minimization procedure. And if we're interested in sparsifying these models, in making them smaller, the first place we might look is with an L1 regularization term, similar to we saw in a couple talks ago. This is known as lasso, and the key property with lasso is that during training, it sets some of the weight values in your model to precisely 0. So I've zeroed out some of the values in our example parameter sets here. But this doesn't take advantage of the structure that we know exists in our model. So instead, we turn to group lasso. Now in the lower left, we've created two separate groups of weights. The first group contains all of the weights in W11, that is, all of the weights in the first transition of that top WFSA. And the second group contains the parameters for that second transition. And the key to group lasso is that it zeroes out all of the weights in one group at the same time. So some entire groups of weights will be pushed to 0. And for us, that means that this removes transitions from our set of WFSAs. So here I've represented that on the right. So how does this apply to, how can we apply this to learning our entire model? First, we'll start with a large parameter-rich initial structure. Then we'll train our model using our group lasso regularizer. And finally, we'll have our learned structure where some of the transitions in our model have been removed and the model has learned the other weights. So we'll be evaluating these learned structures and comparing them against baselines, where in each baseline we manually set the number of transitions. So that's the standard machine learning approach, where we first fix our model structure before training, and then we train that model and evaluate it without changing the structure or the number of weights in our model during the training procedure. As an example, here we show a baseline which has a set of WFSAs that each have only one transition in them instead of two. So for our experiments, we'll be looking at the Amazon Reviews dataset. This dataset includes sentiment analysis. It's a binary sentiment analysis dataset. Specifically in this talk, we're just going to show plots for the kitchen subset. Our approach is reported here in orange, and our baseline is in blue. On the x-axis, we have the number of transitions. And what we can remember is that the number of transitions in our model directly corresponds to the number of trainable parameters in our rational RNNs. What we see in this plot is that as we move from right to left, we are evaluating more sparse and efficient models, and our baselines decrease in performance, whereas our approach, which learns the structure of the model at the same time as the weights, retains good performance even with reasonably sparse models. So these experiments in this plot were run with glove embeddings. We also ran these experiments with frozen BERT embeddings, and we found a similar story where our approach outperformed our baseline. So the takeaway here is that learning the structure allows us to retain high performance even with sparse, efficient models. These results hold in other tasks that we evaluated on in our paper. You can check there to see more. One additional advantage of sparse rational RNNs is that they can be human interpretable. And what I mean by that is that these models recover patterns in our data which correspond to high and low sentiment. So if we look at a single WFSA from our set, then we can find strings to which it predicts high sentiment. For example, definitely recommend or excellent product. And those which it predicts have low sentiment, such as very disappointing or was defective. We have more of this kind of analysis in our paper. You can check there. So in conclusion, we leveraged the WFSA view of rational RNNs to form groups of weights in WFSA space. We then regularized those groups using group lasso and learned a structured sparse model. And we showed that these structured sparse models retain performance of the parameter-rich baselines, and they can be more human interpretable. Thank you.
Questions? Hey, thanks for a very interesting talk. I promise this is a hostile question, but can you clarify why this is learning the structure? It seems to me like, yeah, you're varying the size of the hidden layer, and you're saying, okay, I can make my model more efficient, but you're not really changing like the class of model in any substantial way, or are you? And I'm just misunderstanding.
No, you're right. So we're not changing the class of the model in any substantial way. But we are adjusting the size of the hidden layer and the connections within that hidden layer. So here I'll go back to our slide describing rational RNNs. And this hidden layer here has some internal structure. I'm not representing that too well on this slide, but you can check the related work for more information there. And those connections are what we are removing. So effectively, this is removing groups of weights. And you're right that it's not going to change this to, for example, some other type of model, like something that's not an RNN. But in general, this kind of structured sparsity approach can be used. The sort of take-home message here is that the structure that's in our neural network can be used to form these groups, and then it will regularize some of those groups away, thereby adjusting this structure and the connectivity that we see within our models. Does that make sense?
Okay. Yeah, please.
Thank you. I was wondering, how's in terms of model performance with the size of the network? Is there a comparison with non-rational RNNs with an analog in the number of hidden units? Do you see an increase with the unstructured model with more weights, or do you need more space in the model?
Yeah, so that's a good question. I think we, in this work, primarily focused on rational RNNs. So those were our baselines. There's a number of other, this line of work regularly compares against other types of RNNs. So presumably those results would hold on our data sets as well, comparing the rational RNNs that we learn against other types of RNNs. In terms of the number of parameters required to do well in these tasks, I'm not sure that adding more parameters at the beginning of training, in this case, would lead to better performance. Here we did evaluate quite a wide range of model structures. So I think what we found was, for the structure we had in the data sets that we were looking at, the number of parameters that we had in our sort of maximum parameter-rich baseline was roughly plateauing in terms of performance. And it's not quite BERT level performance, but in terms of comparing against other RNN structures, this seemed to be comparable with the best that we knew of. Yep.
Any other question? Last question.
If someone else has a question, I'm happy to wait until after. Okay. Have you drawn any comparisons with like distillation-based methods for taking an over-parameterized model and then making it smaller through distillation?
Right. So yeah, that's I almost put a slide in at the beginning saying this isn't a distillation method. These are two sort of parallel lines of research, and I think there's rich history here in group lasso and other types of sparsifying regularization. There's also a rich history of distillation and other model compression approaches. Here, we are explicitly removing elements from like connections from a model as we train, and those start with some structure which is fixed, and then have a smaller structure which they train to perform as well as the larger one. I don't know which of these approaches would perform better in this case. I think the main advantage we have here is that the structure in the rational RNN can be leveraged in our groups. Distillation seems like something that wouldn't leverage that that structure within your model. So I don't know in terms of performance which one I could compress our models with more. I will say distillation generally first trains the large model and then trains the smaller model. Once the first is trained to convergence, you train the smaller model on the predictions of the first. Here we only have to do one training run, so we don't have to do first train our large model, then train the smaller one. We train and learn the weights and the connections at the same time. I could combine them, is that what your suggestion was? Yeah, that's not a bad idea. Yeah, we should talk.
Okay, let's thank the speaker again. So this concludes this session. Thank you for coming.